So now the issue is when an acceptor accepts a value. So in the best case, we have a single proposer. And if there is no interference, this proposer should impose its value on the set of acceptors, and we get a decision. So everything will be fine. So our algorithm should work at least in this case. And this is the case that we call obstruction-free progress. You remember we mentioned the notion of obstruction freedom earlier. So what is an obstruction-free execution? It is if a single process executes without interference, it will be able to make progress. Okay, so let us now describe the algorithm step by step until we get a satisfactory solution. So here is the first invariant we want to achieve. We call it P1. We say an acceptor accepts the first proposal it receives because, as I told you, this is the best case, and if there is a single acceptor, it should impose its value. That's the behavior of an acceptor now. It accepts the first proposal it receives. So let us see what is the problem with that. So here's our first attempt. We say acceptor accepts first proposal it receives, but we have the following scenario. We have a set of acceptors, P1, P2, P3, B4, and P5. We have two proposers. One is proposing red, and the other is proposing blue. And P1 to P3, the acceptors accepted the red value. So we have a majority that's accepting the red value. So this is a chosen value. And we have P4 and P5 accepting the blue value. That is fine. An acceptor accepts the first proposal it receives. But then we have a crash event here. So at this point, we don't know which value is chosen. So a learner cannot decide which value is chosen. We have now two reds and two blues. So this solution by itself, accepting the first proposal, is not enough. Let us see this in our ballot array representation. So we have two proposals, P1 and P2, that propose red and blue. And we were here, what we call round one. Round one, we have, this is the state of the acceptors, the red. We have a majority of acceptors accepting red, and a minority to accepting blue. This happened there. But as we said, P3 crashes. So that's what we have now. We have this situation. We have two reds and two blues. So we are in a situation where we cannot distinguish which of the two proposals should we choose. So we need to distinguish between proposals, so each proposal should have a unique number identifier. So here is the first lesson that we learn. Acceptor accept the first proposals, but also different proposals should have unique numbers. So here is the situation. So proposers can try again and propose again because we are stuck. We cannot do anything. And therefore we want to distinguish proposals with unique sequence number or ballot number. And we would like to have these proposals from different proposers, unique proposals. To do that, we want then to have unique proposals. And how can we do that? If we have n nodes, so the first proposer will use the sequence 1, n plus 1, 2, n plus 1, and so on. The second process will use 2, n plus 2, 2n plus 2, and so on. So that is a way to arrange the proposals that they are unique. Another way, of course, to have unique proposals is to have proposal numbers as a pair, a local clock, which is monotonically increasing, of course, or a logical clock, plus a local process identifier. And you use lexicographic order if they collide. So if the clocks collide, choose the one with the highest processor identifier. So that is a possible way to create unique proposals. Okay, so let us now work with the same problem that we have before, but now we give the two different proposals, the red one and the blue one, unique proposal numbers. So we get into this situation where P1 proposes red and it is accepted by acceptors P1, P2, and P3, which is fine. Now P1 and P2 crashes. And now here, proposer P5 proposes blue, and in this case, blue will be accepted, say by a majority of acceptors here. But we have a problem here. So this looks fine. The problem is that at this point here, at this point, learners might decide on red, and at this point here, learners might decide in blue. So we violate agreement again. So this is not enough, what we have done. To see this in the ballot array presentation, we have the following. Here where the acceptors accepted the red, say with number 2, and then acceptor after that at this state, acceptors A1 and A2 crashed, and here where the acceptors accepted the blue value. So at this stage, red is chosen, and at this stage, blue is chosen. So the problem with the previous slides that we have seen is that if we allow restarting, majority might first accept red, and then a majority might later accept blue. So we need to remedy this problem. So this problem can be remedied, and we can ensure agreement if we can enforce the following. The following says that if a proposal is chosen, means that a majority of acceptors have this value, N and V, then every higher number proposal chosen should also have the value V. So we need a mechanism to enforce this condition or this invariant, that if proposer NV is chosen, every higher number proposal chosen should have the same value V. So just to make a bird's eye view of the algorithm about abortable consensus, we have these two conditions. P1, acceptors always accept first proposal it receives. Second, if a value is chosen, V, every higher proposal chosen has the value V. And just informally, P1 ensures obstruction-free progress and validity, because what you decide is one of the values proposed by the proposers. P2, if we can implement it, ensures agreement. And of course, integrity is trivial to implement. Just remember if you have chosen before, and then so you at most choose once. So that is easy. So now let us see how to implement P2. So here is our condition. If a value is chosen, every higher proposal chosen have the value V. How to implement it? Well, one way to ensure property P2 is to have this property P2A, which says if a value is chosen, every higher proposal accepted has the value V. Of course, as you can see, this property implies this property. So P2A implies P2, but we are now in a situation where we are left with this condition. If a value is chosen, every higher proposal accepted has the value V. And observe that acceptors have only a local view. They don't really themselves individually know which value is chosen. So we have to do something here. So here is our problem now. We cannot prevent an acceptor from accepting higher value proposal. So we are here. P1 and P3 has accepted red. P4 and P5 have accepted blue. And we would like to prevent P1, P2, and P3 from accepting blue. Okay, we cannot do that. So the way to solve this problem is to strengthen this property P2A and say the following. What we can do is that If a value is chosen, then every hire proposal issued by a proposer should have also the value V. So we said this is not allowed anymore, this part. We do not allow P4 and P5 to issue a proposal with the value blue. So let us see this in the ballot array representation. In the ballot array representation, we have the following situation. We are at round 3. At round 2, the red value was chosen. At round 3, the proposer P2 has to propose the value red. It cannot issue another value except red. So if we can achieve that, we can make sure that proposer at round 3 proposes the red value, then the red value will be accepted. And if the red value is accepted by majority of proposers, it will be the chosen value.